Hello students, welcome back. The final topic for section 1 of this notebook is the implicit differentiation of inverse functions. Alright, let's begin, and we begin with a preparation. Let's consider a special case. When x and t are the same, it's a bit small here, so let me rewrite it a little bit bigger here. Okay, when x and t are the same, take the derivative, then x prime is, well, what's the derivative of t? That's 1, of course. T is the independent variable, so the derivative of t is just 1. Or, if you prefer, you want to do a little bit more extensive computation like this with the same result. Let's see. X and t are the same, as I highlighted in red. So this t and this x are the same. And what's the result? We have dx dx, and of course that's 1. Numerator and denominator are the same. So how do we apply this special case to a certain example, like this one, for instance, associated to this kind of interesting picture? Okay, let's go ahead and do this with the usual computation. 3x squared times x prime. Remember, by chain rule, whenever you apply the derivative rule to x, x prime pops out. Same thing here. 5y to the 4th power is a derivative by y, and then by chain rule, y prime pops up. And then the derivative of this constant, 3, that's 0. And then we have the product rule. 2x x prime times the second function, and the first function times the derivative of the second function, 3y squared, and the y prime pops up. Okay, that was the implicit differentiation. But then again, remember here, x prime is 1, because x and t are the same. So x prime is 1, so multiplying by 1 won't change anything. And here, x prime again, multiplying by x prime is multiplying by 1, so it doesn't change anything. So there goes the implicit differentiation in a special case, then x and t are the same. Now that was French notation, and if you prefer German notation, here we go. You have to replace this y prime by dy dt, right? And this one too. But then again, x and t are the same in this particular case. We're considering the special case when x and t are the same, all right? So dy dt, here, t is the same as x, so let's write dy dx. Just like we did over here. Dx dt is same as dx dx, consequently it was 1. Likewise, instead of dy dt, let's use dy dx. Either way, it works out. We can do the implicit differentiation like this in a special case when x and t are the same. By the way, we have the answer key here. Oh, excuse me, sorry about that, wrong cell. Okay, here's the answer key here. We can do the computation like this. Okay, and then we can do some further computation. And those kind of topics will be discussed in section 4, which is a little bit aside from our point of interest, so I set it as the optional section. Right now, we consider just one application, that is, the implicit differentiation of inverse function. Okay, here's an example. X is e to the y power, and let's calculate the derivative, dy over dx. Okay, the problem was given in terms of Leibniz notation, the German notation. So let's use German notation in this case. X is e to the y power, and let's calculate using German notation. Oops. So dx is equal to, let's see, a little bit bigger font is in order. We have fraction here. Okay, that looks better. So taking the derivative by x, we get dx, which is of course 1. And then right hand side, derivative of this exponential. Well, by chain rule, outside function first and exponential always remain the same. And by the chain rule, we have to multiply the derivative of the inside. dy dx. Dx is, that's 1, isn't it? So in order to solve for dx dy, this one, flip this exponential to the other side. So dy dx is equal to 1 over exponential. Looks like we have the answer. Not quite. Not quite. 1 over e to the y power is correct, and this entire process is correct, but not the most simplified form, because what did the problem say? E to the y power is x, so the denominator is x. So let me take one extra step. dy dx is 1 over x. And that's how you do this computation. Here's the solution if you open up. Bigger font. Okay. Same computation. I don't need this. Let's come back to this. Now, did I say we were doing the implicit differentiation of inverse function? Does it have anything to do with inverse function? Yes, it does. From here, x is e to the y power. A bit bigger font again. Here, let's take the log of both left-hand side and right-hand side. From here, no, let's do it this way. Copy and paste the entire cell, and then in the second step, we take the log of both left-hand side and right-hand side. All right. Now left-hand side log of x. That's good. And the right-hand side, log and exponential cancel each other out. So we have just y. And what do we have? Y is log of x is equivalent to x equal to e to the y power. You see, inverse function came out. So what computation did I just do here? Well, in fact, we did this computation. Y is log of x. If that's the case, then dy dx is nothing more than the derivative ddx of log of x. And what's the derivative of the log function? We've been using this for a while. It's 1 over x. So what did you just do? We proved the derivative formula of a natural logarithmic function that we had been using for quite some time. I guess that's the only important example I can think of on the implicit differentiation of inverse functions at this level. We have one more example down here, the general case. X is a to the y power, and how do you work it out? I'll leave that as an exercise for you. Stop the playback and try to reproduce something like this. All done? Here we go. A to the y power. Take the derivative. Exponential remains the same. Excuse me, not the same as a matter of fact. This is the derivative formula for arbitrary exponential, and then dy dx pops out, and then you're solving for dy dx. Let's get a little bit bigger font. And then we end up with 1 over x log of a. And that's associated to the inverse function. Y is log a of x. In that case, the derivative formula is 1 over x log of a. Okay, so much for section 1. And we're going to talk about section 2 and section 3 in separate videos. See you soon.